Hello everyone, welcome to this video. In this video, we'll be looking at the proof of fundamental theorem of cyclic groups. So here in the statement, we have every subgroup of a cyclic group that is cyclic in nature. This is the first statement that we have to prove. Next in the theorem here, they say that if the order of the group which is generated by A is equal to n, then the order of any subgroup of the group which is generated by A is a divisor of this n, right? And for each positive divisor k of n, the group which is generated by A has exactly one subgroup having order k, and that is represented by this group where this is generated by the element A raised to power n divided by k. N was the order of the group generated by A and k was sum of the divisor of this n, right? So this was the statement. Now let's move forward and prove this statement over here. So first of all, we wanted to show that every subgroup of a cyclic group is cyclic. So let's see this result first, because here we consider G as some group which is cyclic group, right? So we consider A to be its generator, and suppose that H is a subgroup of G. Now what we wanted to show that this H is also cyclic in nature. So that means this H could also be written as power of some, all the elements in H could be written as power of some element, right? So we'll be proving that thing. So now if H has only one element and that is identity, so obviously it is a subgroup and it is cyclic in nature, because the identity, the singleton set containing only identity is a subgroup, you know, that is a trivial subgroup. Okay, and that is also cyclic in nature. So if this is so, we are done in this case. However, if that is not so, the given subgroup is not the trivial subgroup, it is something else, then in that case we have to prove that this H is cyclic in nature, right? So for that, what we do, we claim that the subgroup H that contains an element of this form A to the power t, where t is some positive number, right? This is our claim. So for that, what we do, we consider a group G, right? Because we have the group G which is generated by A, and we are taking H as a subset of G, right? This is the thing. So that means all the elements of H, they are present in G also. This is H, this is G. So that means all the elements of H are also of this form A to the power t, where t is positive. Hence our claim is justified. Even if this t is negative, suppose we have this form, then also if t is negative, then A raised to power minus t, so minus t would be positive if t is negative. So overall this thing would be positive. So therefore our claim is justified. So we can write all the members of H as A raised to power something, right, where this something is positive in nature. Okay, so using this thing, if we assume that m as the least positive integer such that A raised to power m belongs to H, we consider our subgroup to be of this kind, then we have to show this H is actually the subgroup which is generated by A raised to power m, right? So we are assuming this m to be a least positive integer such that A raised to power m belongs to H. Now according to closure property, this group would be a subset of H. Why? Because we are assuming that A raised to power m belongs to H. So all the members which are the powers of this would be present in H only, right? Next, we wanted to prove that H is contained in the subgroup which is generated by A raised to power m, right? Then only from these two expressions we would have equality between them. So next we claim that this equality, and in order to have this equality here, we wanted to prove this inclusion. So for that, what we do, we consider some element from H and we prove that that element is also present in this subgroup generated by A raised to power m, right, where that element is an arbitrary member. So we call that element as B, and we show that this B is also a member of this subgroup here, right? So now because B is in H, so that is also present in G, because H is a subset of G. right? And G is of this form, which is generated by the element A. So that means the element B could be written as some power of this element A. So let's call that power to be K. K could be anything. So we have written B in this form, which is A raised to power something. So now what we can do, we have this M here, which is the least positive integer, right? And we have this K here, which is some number. So we can apply division algorithm onto both of them, so that we obtain two integers, one is Q, one is R, such that you can write K as MQ plus R, right? Where this R, the remainder portion, is obviously greater than or equal to 0, and it is less than M, the divisor of the division, right? So this is the division algorithm. So here, because K is equal to MQ plus R, so A raised to power K is A raised to power MQ plus R. So you can separate out the terms here, right, according to the exponent laws. And from here, you can calculate what is the value of AR. AR is calculated when you pre-multiply both sides of this equation, this and this, by A raised to power minus MQ. So in when you multiply it with A raised to power minus MQ, and with here also this term becomes identity, so this becomes AR here, and on the left hand side you have this term, which is this term, right? So you have AR is equal to A raised to power minus MQ, A raised to power K. Now because A raised to power K was your B, and this is a member of H, and moreover A raised to power, so this is a member of H, one thing. Another thing, A raised to power minus MQ could be written as A raised to power M raised to power minus Q, right? So because you know what is your H is generated by A raised to power M, so that means this thing is also present in H, right? Therefore, because both of them, they are present in H, therefore this AR is also a member of H. So that means we now obtain an integer R such that it lies between 0 to M, and AR belongs to H. However, for the definition of H, we have assumed that M as the least positive integer such that A raised to power M belongs to M. But now we obtain R which is less than M, which such that AR belongs to H. So now this is a contradiction, so this thing cannot be there. So therefore R should be equal to 0. R cannot be any other number, because if we take any other non-zero number, R as any non-zero number, then in that case the condition does not hold here, our assumption does not hold here. So because M was the least positive integer such that A raised to power M belongs to H, so therefore A raised to power R cannot belong to H. So that means R should be 0. If R is 0, in that case your K would be MQ only, because earlier it was MQ plus R, R is now 0, right? So it is MQ only. So B would be written as A raised to power K, and K is your MQ. So you can write this MQ as A raised to power M raised to power Q. So it is written as some power of A raised to power M. So that means it would be member of this subgroup which is generated by A raised to power M. So we have started by taking this B from H, and now we have reached at a point where we say this B is a member of A raised to power M, and this B was an arbitrary member, so that means all the members here are also present here, so that means H is contained in the subgroup generated by A raised to power M. And earlier we had A raised to power M contained in H, so from both of them we have the equality here. So this proves that H is equal to the subgroup which is generated by A raised to power M. So we can say that H is cyclic in nature. So this proves the first statement of this theorem here, right?